Imagine a future where artificial intelligence could not only learn, but actually teach itself how to learn better.
Hmm.
Picture a really diligent student, right, who doesn't just passively read a textbook, but actively takes their own notes, reorganizes the information, figures out the absolute best way to study for new challenges. What if LLMs could do that?
That's precisely the really intriguing idea we're diving into today.
Welcome to the Deep Dive, where we take complex ideas from your sources and distill them into essential, surprising insights to get you well-informed quickly. Today, we're taking a deep dive into some, well, truly groundbreaking research from MIT. It's about how language models might be moving beyond their current kind of static capabilities.
Right. Our focus today is on something called self-adapting language models, or SEAL for short.
SEAL. Okay.
And the mission really of this deep dive is to unpack this innovative framework. It enables large language models to generate their own training data and even their own learning procedures.
Their own procedures. Wow.
Yeah, and this leads to something pretty remarkable: persistent self-improvement.
Okay, so let's get into the core problem SEAL's trying to solve then. Because large language models, they're incredibly powerful after that initial training, right? But they are inherently static.
Exactly. They lack those built-in mechanisms to truly adapt their underlying knowledge or, their skills when new information pops up or new tasks come along.
Right. Think about it. Once they're done training,
Yeah.
they're just using what they've got.
Precisely. And this creates a real bottleneck. When new data emerges or specific tasks arise, you suddenly need these massive tailor-made data sets.
It's a lot like how you prepare for an exam, isn't it? You don't just passively read the textbook.
Not at all. You might summarize, maybe draw diagrams, rewrite concepts in your own words, create flashcards, whatever works for you.
That active transformation is key.
It is. You reformat and augment the information in ways that make it easier for you specifically to understand and remember.
But current LLMs, they typically just consume data as is during
Yeah.
fine-tuning, right?
That's the standard way, yeah.
So the big question this research tackles is, can LLMs do what we do? Can they self-adapt by transforming their own training data and learning procedures?
And the answer, thanks to this research, seems to be a resounding yes.
Okay, let's unpack SEAL then, this breakthrough idea.
Right. So researchers at MIT introduced SEAL, this framework that basically empowers LLMs to become their own teachers.
Their own teachers.
Instead of relying solely on external data and, human-defined fine-tuning steps, SEAL allows the LLM to generate its own self-edits.
Self-edits.
Mm-hmm.
That sounds really innovative. Can you unpack that a bit? What exactly is a self-edit coming from an LLM?
Sure. Think of them as natural language instructions or directives. They specify how the model should update its own internal weights.
Okay.
So they could include, say, restructured information, optimization hyperparameters like learning rates, or even specific commands to augment data in a certain way.
So it's like the model writing its own personalized study guide and the instructions on how to use it.
That's a great way to put it, yes.
So the model isn't just spitting out more data, it's actually changing its own approach to learning. Like deciding, okay, for this task, I need to learn faster, or I need to look at this data differently.
Exactly that. It's about self-configuration. So for instance, in that few-shot learning scenario we'll talk about, the model might generate an edit saying, apply a 90-degree rotation to all the training images.
Huh?
Because maybe it found that's a useful strategy for a certain kind of abstract puzzle. Or it might say, set the learning rate to 0.0001 for this specific task. It's like writing its own dynamic best practices guide.
That's fascinating. So how does this self-teaching actually work under the hood? Is there a core mechanic?
There is, and it's quite elegant, actually. The research describes this two-loop system.
Okay, two-loop.
The first is the inner loop. That's the self-fine-tuning process itself. So the LLM generates a self-edit.
Right.
And that self-edit then guides a supervised fine-tuning process, SFT. And this results in actual persistent updates to the model's parameters. Its weights actually change.
Okay, the inner loop sounds foundational, getting the change made. But I imagine the real magic might be in how it refines those edits over time. What happens next?
That's exactly where the outer loop comes in. And this uses reinforcement learning, or RL.
RL. Hey.
So after the model updates itself using one of those self-edits, its performance on some downstream task is evaluated. Like, did it answer the question correctly?
That makes sense.
That performance acts as a reward signal, which the LLM then uses through this RL process to improve its strategy for generating future self-edits.
So it's literally learning how to learn more effectively.
Precisely. That's the key.
Okay, understood. And that's a crucial distinction, right? Because unlike maybe previous approaches that use separate modules or something, SEAL directly uses the model's own generative abilities to control its adaptation.
Exactly. It's not bolting something on, it's using the core capability of the model itself.
It's like the student not just studying, but actively figuring out the absolute best way to make their own study guides and even the optimal way to use them.
You got it. That's the analogy.
So we've got the how. Now let's talk about SEAL in action. This sounds like it could have some really profound real-world applications. What kind of striking results did they actually see?
Yeah, they tested it thoroughly. The researchers evaluated SEAL in two pretty distinct use cases. The first was knowledge incorporation,
Knowledge incorporation.
which basically focuses on getting an LLM to reliably recall new factual information without having the original source text right there in its immediate context.
Oh yeah, that's notoriously hard for current models. Remembering something new you just told them outside the immediate chat window.
Exactly, it's a huge challenge. So SEAL's approach here was different. Instead of just fine-tuning on a raw passage of text,
Which is the usual way.
right, instead, SEAL prompts the model to generate implications derived from that passage.
Implications.
Yeah, like drawing conclusions or rephrasing the key points. This self-generated synthetic data, remember, that's the self-edit, is then used for the actual fine-tuning.
Interesting. So the idea is that by re-expressing the knowledge in its own terms, the model internalizes it better.
That seems to be the core idea, yes.
And the proof. Did it actually work? How much better was it?
The results were quite compelling, actually. They used a model called Qwen 2.57b
Okay.
on a standard question answering task, SQUAD, but with no context provided at test time, so it had to remember.
Right. A tough version.
Yeah. And fine-tuning on just the raw passage, it offered a pretty negligible gain. Went from about 32.7% accuracy for the base model to just 33.5%. Barely anything.
Okay, so standard fine-tuning didn't help much.
Not really. But when they trained it on the self-generated synthetic data via SEAL, the accuracy jumped significantly, all the way up to 47.0%.
Or 47%.
Yeah,
That's a massive leap from 33.
it really is.
It almost sounds like this smaller model, by learning to teach itself effectively, got smarter in a way than just feeding raw data to potentially even a larger model.
Right.
Is that fair?
That's a key insight here, I think. It really challenges that assumption that just scaling up model size or data volume is the only path forward.
Right.
SEAL shows that how a model learns, how it processes information through these self-generated insights, can be a much more efficient and potentially more powerful path to actually retaining knowledge.
And did they compare it to other ways of generating synthetic data?
They did, and this is crucial. The self-generated data from this smaller Qwen model actually outperformed synthetic data generated by the much larger, very capable GPT 4.1 model.
It beat GPT-4's synthetic data.
Yep. GPT 4.1 reached 46.3%, while SEAL with Qwen hit 47.0%. And these improvements held up even in a sort of continued pre-training setting with 200 passages, where SEAL still got 43.8% accuracy.
That's really impressive.
And qualitatively, you could see it learning. As the RL training progressed, SEAL learned to generate much more detailed and effective self-edits. It went from simple rewrites to these extensive lists of implications.
So it got better at teaching itself over time.
Exactly.
Okay, that's fantastic for remembering new facts.
Right.
What was the second use case you mentioned?
Right. The second one was few-shot learning. This is all about enabling LLMs to quickly generalize to totally new tasks after seeing only a handful of examples.
Like humans do, we pick up new skills pretty quickly sometimes.
Precisely. It's trying to mimic that rapid adaptation.
And this involved those abstract reasoning puzzles, like with colored squares and patterns.
Exactly those. They used a simplified subset of the abstraction and reasoning corpus ARC-AGI benchmark. Lots of visual pattern tasks.
Okay.
And in this setting, SEAL's role was to autonomously configure its own adaptation pipeline. It generated self-edits specifying which data augmentations to apply.
Like rotations or resizing you mentioned.
Yeah, things like that. And also what optimization parameters to use, like the learning rate or the number of training epochs for that specific task.
So the model was essentially deciding the optimal way to train itself for each new puzzle.
Yes, that's the remarkable part. It figures out its own best training recipe on the fly.
And the results, how well did it do?
The proof is definitely in the pudding here. Using a Llama 3.21b instruct model, SEAL achieved a really remarkable 72.5% success rate in correctly adapting to these new ARC tasks.
72.5%. How does that compare to other methods?
It stands in pretty stark contrast to the baselines. Test time training without that prior RL optimization only got 20%.
Okay.
And standard in-context learning, just showing the examples in the prompt, that got 0%. Flat zero.
Wow. So SEAL made a massive difference.
Huge. Now, it didn't reach the Oracle TTT. That's where humans handcraft the perfect configuration, which gets 100%, but 72.5% shows really significant progress towards autonomous adaptation.
That's incredibly impressive, seeing it work so well across different kinds of challenges, knowledge recall and fast task learning. These results are so compelling. They really make me want to understand how SEAL actually pulls this off. Can you give us maybe a slightly deeper glimpse under the hood,
Yeah.
the core mechanisms enabling this?
Sure. So the reinforcement learning part, that outer loop, it's implemented using an approach called RESTM.
RESTM. Okay.
You can think of it essentially as a kind of filtered behavior cloning, or maybe rejection sampling plus SFT.
Okay. Break that down a bit.
Basically, it reinforces only the self-edits that actually lead to positive performance improvements. If an edit makes things worse, it gets rejected or downweighted.
Ah, I see. So it's like a smart filter for learning strategies. A student tries 10 study techniques. RESTM figures out which ones actually improve the grades.
Exactly.
And tells the student, okay, generate more techniques like those successful ones next time.
That's a perfect analogy. It's how SEAL consistently refines its own teaching methods over time.
Got it. And what about efficiency? Because fine-tuning, even guided fine-tuning, can be pretty resource-intensive, right? Especially if it's happening potentially often.
Absolutely. And efficiency is crucial for making these constant self-updates practical. So it uses low-rank adapters, or LoRa.
LoRa, right. Heard of that.
Think of LoRa as allowing the model to fine-tune a specific skill or update a piece of knowledge without having to, like, rewrite its entire brain.
More like adding a targeted note in the margin.
Kind of, yeah. It makes each self-edit application really lightweight and practical. This allows for that continuous iterative self-improvement without a massive computational cost every single time.
Okay, that makes sense. So SEAL is clearly a significant step forward. But, as with any groundbreaking research, there are always limitations, challenges still to address. What are some of those, and how does this all fit into the bigger picture of where AI might be heading?
That's a great question. One key limitation, and it's a classic one in AI, is catastrophic forgetting.
Ah, yes. Learning something new makes it forget the old stuff.
Exactly. Where new learning can cause the model to forget previously acquired information, SEAL is still susceptible to this, especially when you perform many sequential updates. Doesn't seem to completely collapse, but performance can degrade on older knowledge.
So that's an area for future work.
Definitely. Maybe by explicitly penalizing forgetting during the RL process, or integrating specific continual learning strategies designed to combat this.
That makes sense. But practically, how do you ensure the model doesn't, say, study ineffectively, or even start generating bad study guides that distort its knowledge if it's making its own learning procedures?
Well, that's where the reinforcement learning in that outer loop is really critical.
The reward signal.
Precisely. The model only reinforces self-edits that lead to actual, measured performance improvements on the task. If a self-edit makes it perform worse, that strategy gets penalized. It's less likely to be generated again.
So there's a built-in quality control loop.
Exactly. It's a continuous feedback loop pushing it towards effective learning strategies, not just any strategy.
Got it. What about the practical side? Is this computationally cheap to run now?
Not yet, no. The computational overhead is still considerable. That process of evaluating each potential self-edit, which involves fine-tuning and then running inference, takes around 30 to 45 seconds per evaluation on their hardware.
Okay, so not instant.
Definitely not. Scaling this up efficiently will require further optimization work.
And the evaluation itself sounds like it needs specific tasks.
It does, currently. That's the context-dependent evaluation point. Right now, SEAL needs explicit tasks that have built-in ways to measure success, like question-answering pairs or puzzle solutions.
Right.
To scale this up to just learning from, say, vast amounts of unlabeled text data, future versions might need the model to learn to generate its own evaluation questions or metrics, which is, well, that's a whole other fascinating research direction.
Generating its own tests.
Yes.
Wow. Okay, this raises a really important question, though. Why is this research so critical right now? Why does this matter for us, the listener, and the future AI tools we'll interact with?
Yeah, it connects directly to something researchers are increasingly worried about, the data wall.
The data wall.
Yeah. Projections suggest that the frontier large language models, the biggest and best ones, will likely have consumed pretty much all publicly available high-quality human-generated text by maybe 2028.
2028, that's really soon.
It is. And once that happens, once we run out of new human text data to feed them, progress might stall unless the models can generate their own high-utility training signals.
So SEAL isn't just about making smaller models better. It's about giving AI a path to keep improving when we literally run out of human data.
That's a huge part of the motivation, yes. It's about sustainable AI progress in a data-constrained future.
That's a truly profound implication. Imagine AI that isn't limited by the existing pool of human knowledge, but can effectively generate its own, building on what it already knows.
Exactly. Picture a future where an LLM could ingest, say, a batch of new scientific papers,
Okay.
and then generate large quantities of explanations, implications, connections to existing knowledge, all for itself, using its own internal reasoning.
A self-study loop.
A kind of iterative loop of self-expression and self-refinement, as the paper puts it. This could allow models to continuously improve, maybe especially on rare or niche topics, even without constant new external human supervision.
That vision is pretty incredible. And how might SEAL interact with other AI techniques we already use?
Well, it could potentially complement things like chain of thought reasoning or COTE-Lee.
How so?
A model might, for instance, choose to perform a quick weight update using a self-edit mid-reasoning to maybe guide its current thought process better. Or, after completing a complex reasoning chain, it could generate a self-edit to distill the key insights into its parameters for future use.
So it's about making the learning more deeply internalized, more part of the model itself.
Exactly. More effective, persistent learning.
And I can definitely see how this ties into the whole idea of agentic AI systems models that need to operate autonomously over long periods.
Absolutely. This framework looks incredibly promising for building those kinds of agentic systems. Models that interact dynamically with an environment and, crucially, need to incrementally acquire and retain knowledge as they act.
So an agent could have an interaction.
Right, and then synthesize a self-edit afterwards to refine its behavior or understanding based directly on that specific experience. It's a foundational step towards AI that's truly adaptive and genuinely self-evolving.
Okay, so summing this up, what does this all mean? The big takeaway from this deep dive seems to be that SEAL fundamentally demonstrates that these large language models don't have to remain static.
Correct.
By learning to generate their own synthetic data, their own learning procedures, and apply them through these lightweight updates, they can autonomously incorporate new knowledge and adapt to novel tasks.
It's a really significant step towards truly self-learning, evolving AI, especially as we approach that potential data wall.
It truly is. It's a shift, like you said, from just passive consumption of data to active self-directed learning.
Yep.
So what we've really unpacked today is this vision of LLMs that aren't just, processing information, but actively metabolizing it, learning to optimize their own internal understanding and skills. It feels like a leap towards truly adaptive and self-improving AI.
I think that's a fair assessment.
And just pausing on that, a self-adapting model, potentially smaller, outperforming a much larger one on certain tasks, that really makes you rethink the whole future of AI scaling, doesn't it? Just bigger isn't always better.
It certainly suggests alternative paths. And, consider this as a final thought. If language models can genuinely learn to teach themselves effectively, generating their own knowledge, refining their own learning strategies, how might that fundamentally change our relationship with AI? What happens when these systems become not just intelligent, but continuously self-evolving entities, potentially reducing their reliance on direct human input for their continued growth?
A fascinating and maybe, slightly unsettling thought to end on. It points to a future that seems to be taking shape much faster than we might think. We hope this deep dive has given you a fresh perspective on the really dynamic future of artificial intelligence.